Welcome to session 13, part 2 on beams. In the last part of this session, we discussed deformation and how to relate radius of curvature to longitudinal strain. In this part of the session, we're going to discuss how to be able to relate bending moment to bending stresses or longitudinal stresses. So we hop right in to some math and some visuals for what is happening with longitudinal strain as we described in the past session. So if we take a side view of a beam, what we see is that there is a neutral axis given by this x, and there is going to be some strain above and strain below this neutral axis with an applied bending moment, and that it may be that above the neutral axis we have compression or a negative tensile strain, and below we have a positive tensile strain. And we can describe the strain that we're experiencing at different parts of this beam or different heights away from the neutral axis as follows: as minus y over c times epsilon max, where epsilon max is the maximum strain that's being experienced at one of the surfaces. Now, if we're interested in getting to stresses, maybe we should bring out our friend Hooke's law. And in this case, we're discussing Hooke's law relating to sigma and epsilon through the elastic modulus. So sigma equals E epsilon. So here we get to a form. This is not the final form, but a form of bending stresses that can be slightly useful. So just as we had this expression describing how we have an absolute maximum bending strain at the surfaces, okay, so as the distance from the neutral axis approaches often half the height, okay, or the distance to the surface, we have that same ratio, but now being applied to thinking about having a maximum bending stress, say sigma max, and relating it to sigma. As we see here in this diagram, we can draw the same exact one, except now we're replacing epsilon that we had here, or the strain, with sigma. And we have a sigma max, say, at the surface, and we have a linear change or a slope reflecting the bending stresses within the material. And we can further simplify this expression if we just say, okay, there's an E on both sides, and we have something that's very similar to what we had with the strain, now with the stress. Okay. So that's helpful, and remember that this is kind of how we started discussing the possible ranges for the shear stress and shear strain in a twisted shaft. But we want to get to the point where we're connecting this this moment, okay, the load that we're interested in, to the actual bending stresses and strains. So let's go a little bit further in our derivation. And here we're going to discuss what a cross-section looks like with stress on it. Okay, a cross-section, so we take a cut of the beam and we see that with this applied moment, okay, or internal moment, okay, sorry, for this internal moment that is kind of being applied to this cross section, we see that the top portion above, let's say this neutral axis right about here, is going to be in compression. So these purple arrows are going into the material, reflecting a compressive stress. And then below, we have a tensile stress coming out, okay? So we've kind of saw this, right, when we were taking the cross section, we're looking at compressive strain and tensile strain. Let's write the expression that we just derived, where we have sigma is equal to minus y over c times sigma max. Okay? Again, signifying that we have a gradation in the stress, okay? But we would need to know the maximum stress in order for this to be useful. We can then use this idea that this surface is not going to be accelerating, and that about the neutral axis, if we do a summation of all these little stresses over areas, okay, if we were to look at this, that the net result, okay, of the force on this area, not the moment, but the net result on the force on this area should be equal to 0. Okay. And you can think about how we've looked at beam bending problems in the past, where we have a shear force and we have a bending moment. And typically, unless there's a load coming axially from the sides, we're saying that there's no axial force in the material. So this needs to come out to be equal. This integration, essentially, of all these little pieces of stress acting over these small areas, that needs to come out to have a resultant force of 0. So to do that, we say, okay, we're going to integrate this stress over the dA, and that over the entire area, but sigma dA over the entire area. So we plug this expression in that we have sigma equals minus y over c sigma max. We then write out this integral, and this is a constant, the sigma max over c, so we can bring that out, and we're left with this expression where this is a constant and this integral has to be equal to 0. This integral or over a of y dA is something that we call the first moment of area, okay? And in this case, it's being forced to be equal to 0. We will not go into detail on the calculation or the utility of this quantity for calculating shear stresses. Okay, we're going to calculate shear stresses in the next section. And we'll also kind of skip for now how helpful this expression is for determining the location of the neutral axis. But in the next session, when we discuss transverse shear stress, we'll take some time to break down the first moment of area in more detail and show some examples of how we might use it to do these two things listed here. We're actually going to focus more on what's called the second moment of area in just a second, and in the next part of this session. So we've now done equilibrium for the resultant force, okay, setting that equal to 0. Let's look at equilibrium with the moments. Now, in this case, we do have a moment being applied, or an internal moment being applied to the surface. So when we look at summing all the stress-based contributions to moment, it needs to equal this internal moment m. Okay, so that's what we have here. So we could have said summation of all these individual quantities minus this internal moment is needing to be equal to 0. That would have been fine. Or we can say, hey, they're all being summed up to equal m, is what you have here. Now, what do we do? So remember before, for the stresses coming out to forces, we just did integral of sigma dA. But to figure out moments, what we can say is this sigma dA is some distance y, right? This is the vertical direction, y above the neutral axis. And so it's going to be contributing a torque. In this case, if this is compressive going in at y, and this is z, it's going to contribute, this little element right here is going to contribute a positive moment, right, in the same direction as m. So we have this same expression that we derived previously, and we can plug this in to our equation right here, and we get the following. We get that the moment, the internal moment, can be thought of as being equal to a constant times an integral of y squared dA. This second moment of area, okay, or the integral of y squared dA is the second moment of area. This gets its own variable. We call it I, okay? And we use this I quite a bit when we're looking at bending stresses. Now, let's go ahead and substitute in, instead of writing this integral of y squared dA, we're just going to put an I in there, and we're going to say that the internal bending moment is equal to minus sigma max over c times I. Okay, and from this expression, we can then, remember we weren't able to solve for the sigma or max, or we didn't know what sigma max was. We knew what sigma could be as a function of distance away from the neutral axis, but we didn't actually know what sigma max was. So we now have an expression with sigma max and m. This is a kind of a neat moment where we're able to relate the internal bending moment to the bending stresses. So sigma max is equal to, with a rearrangement, negative mc over I. Now c, right, remember that's the distance to a surface from the neutral axis. We can plug this now back into this equation. When I say this, I mean sigma max into this equation here that has sigma max in it, to then figure out what the bending stress is as a function of a distance, okay, from the neutral axis, the applied, or the internal bending moment, which is also dependent on the applied moments to the system or forces, divided by the second moment of area. This is a huge equation. This is one that you want to remember if you're going into a job interview, okay? Because if you have a beam and there's some bending moment that you can calculate, you're able to calculate an axial stress. And it actually has a special name that I'll add here called the Flexure formula. Okay. So this is definitely one to write on your notes or memorize. To finish up this portion of the session, we have a problem, and I guess I have slightly cut off the problem, but I'll just read it for you. For a beam with length L, height h, and second moment of area I, loaded with force P as shown in the diagram, what is the maximum bending stress in the beam in units of megapascals? Okay, so take some time, use the relationships we just discussed to see if we can both pinpoint where that maximum bending stress should be. Hint, hint, it's where the maximum bending moment might be, okay? And it's probably at a top or bottom surface, and it's fine if, you might have a compressive one and a tensile one, but we're just looking for the max, so take the absolute value if it's negative. And that concludes the session. Or not the session, just this part of the session. Thank you.